Good evening. Happy, very miserable, wet Wednesday. So, two quizzes down. Midterm next week. We're almost at the halfway point. That's exciting. For the code, I'm going to give you the chance to fix it and turn it on the 13th. We're looking at arc length and surface area. So what is arc length? Arc length is just length of a curve. So let's say we're given some curve represented by f of x. Arc length from A to B is just the length of that curve from A to B. So you can think of it also as distance you traveled over that interval. How do we find it? This is the more common notation, a little less, to represent length.
Is it 1 under the square root?
That's a 1, yes. I may also use L of to represent length. It's just the integral from A to B, square root of 1 plus f prime of x squared dx. These integrals tend to get really ugly. So you may be relying on a CIS to evaluate those quite a bit. We gotta find the length of the curve x equals 3, y to the 3 halves minus 1, from y equals 0 to y equals 4. In this case, our function is a function of y. We want x prime. So what is x prime?
Nine over 2 squared root of y.
9 halves, y to the 1 half. I'm going to keep it as that. This will then be our length. Square root of 1 plus x prime squared dy from 0 to 4. X prime, 9 halves, y to the half. Nine halves y to the 1 half squared is what?
You want over 4.
Yeah. How would you evaluate that? This is an easy use of problem. Just change a variable. Derivative of 1 plus 81 over 4y. It's 81 over 4. So we have to multiply by 4 over 81 times, now, antiderivative of u to the 1 half.
Was it 2 u to the 3 halves? Oops.
2/3 u to the 3 halves, right?
Yeah, 2 u to the 3 halves.
Evaluated, y goes from 0 to 4. $81 times 3, 243. We get 8 over 243 times. So when y is 4, 1 plus 81, 82, right? And then when y is 0, we just get 1. While that is technically acceptable, typically don't leave it in that form. $82 to the 3 halves is the same as 82 square root of 82. So the question is, square root of 82, can that be simplified? 82 is what? 41 times 2. 41 is prime.
Yeah.
So no, it can't be simplified. So that's typically how we would write it. That was on tame arc length. Length of the curve 24xy equals x to the 4th plus 48 over the interval x equals 2 to 4. We're going to need y prime in this case. Two ways we can go about this. Y is simple enough to solve for, isn't it? You could solve for it first, and then take y prime. Would simplify to x cubed over 24 plus 2 over x, right? And then you could easily find y prime from that. You could also do implicit differentiation. So remember how implicit works? d dx on both sides. Derivative of x times y with respect to x. And then we have 4x cubed over there. Problem is, we still have that bloody y to contend with. Which means we'd have to do that anyway. Which is a bummer. So I'm not going to continue that route. Sad face. So still that y there. This is easy enough to solve. 3 over 24. 1 over 8, right? And that would be negative 2 over x squared. Write it as a single fraction. X to the 4th minus 16 all over 8x squared. Our length, integral, interval 2 to 4. Square root of 1 plus y prime squared dx. Oh boy. X to the 4th minus 16 squared.
That like a difference of squares.
X to the 8th minus twice the product. (16 squared). Eight x squared 64 x to the 4th. Oh, that looks hideous. Write that as a single fraction. 64x to the 4th minus 32x to the 4th.
32x.
Plus 32x to the 4th, right? Yeah. Still kind of looks hideous. But it's actually not.
It looks like you kind of just changed the minus to a plus, but you got rid of the 1. Okay.
This is quite sexy.
Can we do sub like x to the power of 4 or something like that? Can I simplify it a little bit now?
You would not be able to do that because you don't have a 4x cubed. You don't have an x cubed dx.
Oh, yeah.
So that wouldn't work. What's the difference between this and that? Minus 32 and positive 32, isn't it?
Yeah.
Wasn't this that quantity squared?
Yeah.
So isn't this that quantity squared, except that minus is a plus.
Yeah.
Well, look. Over the interval 2 to 4, x to the fourth plus 16 is positive, right?
Yeah.
So the square root of that is just x to the fourth plus 16. Square root of 64x squared. Well, again, over 2 to 4. I'm sorry, not x to the fourth. 2 to 4, x squared is positive.
Yeah.
So wouldn't this just be 8x squared?
Yeah.
Well, isn't that integral nice? X to the fourth over 8x squared, just x squared over 8, right? Plus 16 over 8x squared would be 2 over x squared. That is just Calc 1 power rule on both counts. Antiderivative of x squared over 8 is what?
X over 24.
Antiderivative of 2 over x squared.
Two x to the power of minus 1.
You said negative?
Negative 2x to the power of minus 1.
And just minus 2 over x. Evaluate that from 2 to 4. Four cubed over 24 is 4 squared over 4. No. 4 squared over 6. Sorry. 16 over 6, 8 thirds. Two cubed over 24.
8 over 24, 1/3.
Just 1/3, I could do it even easier.
Yeah.
It's just 2 over 6, right? Because this is 4 times 6 and 2 squared is 4, which is 1/3. Answer either way. 2 over 4 is a half minus negative 1. That's a half. That's 7 thirds. 7 thirds plus a half. It'd be what, 14 plus 3? 17 over 6? There's our length. 1706 units. Whatever those units happen to be. So that worked out very nicely. That is coincidence. Yeah, for the most part, the problems that we're going to do are relatively simple to do by hand. That's probably 0.01% of the problems. Most of them are actually really ugly integrals that you are going to use the CAS for. The catenary, I think it's pronounced.
Is that a quiz question?
Might have been. I think you might have had to deal with the catenary curve. Not length, though.
Yeah.
So find the length. Y equals a over 2 times e to the x over a plus e to the minus x over a from 0 to a. So that curve is called catenary curve. And it's a very familiar curve. You should all be, actually I guarantee you all know it. You've all seen it. In fact, I guarantee you saw it today on the way in. We'll look at that a little bit later. There is another way that the catenary curve is defined. So first, let's just re-examine sine and cosine. So we're familiar with cosine theta, sine theta, right? There's actually another way of representing them. Cosine of theta. E to the I theta plus e to the negative I theta all over 2, where I squared is defined as -1. Sine of theta. E to the I theta minus e to the minus I theta all over 2i. These can be derived from Euler's formula. Which says that e to the I theta is cosine theta plus I sine of theta. Notice what this says about sine and cosine.
Imaginary numbers?
They're complex valued functions.
Yeah.
Oh. That's interesting. This is why we don't call them imaginary, by the way. 95% of the results from quantum mechanics involve e to the I theta. Or involve I in some aspect. So how can it be imaginary if quantum mechanics, 95% of the results involve it? That's why we call them complex, not imaginary. Well, then obviously the natural question would be, what if we just remove I from those equations? So if we turn these into real value functions by removing the I, is there an equivalent? And the answer is yes. They're called the hyperbolic trig functions. E to the x plus e to the minus x over 2. We call that the hyperbolic cosine. E to the x minus e to the minus x over 2, we call that the hyperbolic sine. And then there's an entire branch devoted to the study of the hyperbolic functions. And they have properties much like the trig functions do. So hyperbolic sine over hyperbolic cosine is hyperbolic tangent. You have the inverses as well. They're defined the same way. Hyperbolic secant, hyperbolic cosecant, hyperbolic tangent. The Pythagorean identities is where they start to differ. It's no longer sine squared plus cosine squared equals 1. If I remember correctly, I think it's hyperbolic sine squared minus hyperbolic cosine squared is 1. I think that's the proper order. Let's double check that. No, it's the other way around. Hyperbolic cosine squared minus hyperbolic sine squared is 1. So you're going to have similar identity types, right? So you're also going to have like the product, the sum to products, double angles, all those. Just might be slightly different. But you also have identities for that. And the fun doesn't stop there, by the way. There's also spherical functions. Spherical trig functions, which are even more fun than the hyperbolics. Most of you won't have to deal with that. We had this discussion. You will have to deal with it when you take non-Euclidean geometry, also known as college geometry. Yeah. High school geometry was a lie. Euclidean geometry is a lie. It deals with a flat plane. Yeah. Guess what? The universe isn't flat. It's curved. So you should be using spherical geometry. Because when you get near a black hole thing, then it becomes hyperbolic. So you may also see the catenary defined as a times the hyperbolic cosine of x over a. Two ways of defining the same curve. For the demonstration, I am going to use that definition because it's easier to type in, right? Less to type in. So let's say I'm going to define catenary curve as a function of A. This is going to be plot A times hyperbolic cosine of x over A. X goes from I'll do it this way. Minus A to positive A. Why not? That should be all I need. So let me just set that. So what I can do is I can now start doing like catenary of 4, if A is 4. What does that look like? Looks like that. Now, what happens make that minus 50 to 50 instead. Ah, okay. Before I even do that, no, let's do that. And so obviously I'm going to change the plot range as well. Right, and this is going to now make you see what's wrong with the original plot. Let's change that 0 to 50. And so that original plot that was up there, the axis, the origin wasn't 0, 0. Which is why it looked like it was just a regular parabola. So what I'm going to do now is go back to here, but I don't want it to be A. Let's just make it 5 units away from A. On either side. I'm going to get rid of that, but what I am going to do is make the origin at 0, 0. Rerun that, but then I want to do something cool, the manipulate function. stick with 1 to 20 and up it by 1 each time. I may want to actually adjust the plot range. How did I do it before? I stuck the plot range 0 to 100 originally. So unfortunately, this doesn't give me an actual play option. All right, so on the actual desktop version, you can actually play the animation and it ranges through it automatically. Here I have to actually go through it manually. But what the manipulate does is, as you can see, it gives you a slider for your manipulation variable. So you can see how changing that value adjusts whatever the command is, in this case, the curve. So that's probably one of the best views for you to recognize the curve. Where do you see that kind of curve every single day?
It looks like a smile.
I could actually put big dots for eyes. You can do that in Mathematica.
X squared.
Similar, but not quite. Think roadside.
Maybe like taking like X or something?
Power lines
Okay.
between the poles. They form a catenary curve. The arch in St. Louis is also a catenary. So this occurs a lot, especially if you're an electrical engineer. You get to deal with these curves a lot. But I think actually it'd be more civil. They're the ones who actually deal with hanging the power lines. The electricals just deal with actually making them and making sure the
Yeah, it's circular.
current and everything runs through properly.
Yeah, and so we have to account for a lot of things like shrinking, bending.
Mm-hmm. That would be, I don't know if that's so much civil. That wouldn't be electrical either. That would be something else to deal with the heat running through the materials that you have to use to prevent it from.
Oh yeah, it all depends. Yeah.
That's a different branch of engineering. Might be mechanical.
Isn't it industrial because they choose the materials and they write everything like this? That's what I've heard at least.
No, I'm not 100% sure. But it's a bunch of different branches. Way above my pay grade. So this is the length we're going to find. We're going to find a formula for the length of an arbitrary catenary curve. Right, obviously, though, for the actual calculus and calculations, I'm going to have to use the a over 2 quantity e to the x over a plus e to the minus x over a, because we didn't study the hyperbolic functions in this course. If we did, this would be a hell of a lot easier. I think when I rewrite my notes for calculus, I am going to put the hyperbolics back in. Those are so useful. I think we can safely assume that a is greater than 0. I don't know if that's actually necessary for this. We need y prime. Easy way to do it. Constant times an entire function. So when you take that derivative, the constant stays the same. It's the constant times the derivative. Right, remember that? Constant multiple rule. This way I don't have to actually distribute the a over 2 through to both terms. Derivative of e to the x over a.
Is it e to x over a?
Close. You forgot chain rule.
And e to the x over a?
Not a.
One over a?
1 over a. E to the x over a. Derivative of x over a. 1 over a. What about e to the minus x over a?
And then 1 over a e to negative x over a.
Can factor out 1 over a. Be left with 1/2 e to the x over a minus e to the minus x over a. By the way, looking at those definitions, you should easily see that the derivative of hyperbolic cosine is the derivative of hyperbolic sine. The derivative of the hyperbolic sine is hyperbolic cosine. Right, so you lose the negative. Derivative of hyperbolic cosine is hyperbolic sine. Derivative of hyperbolic sine is hyperbolic cosine. That's why I said this would have been a hell of a lot easier if I could use the hyperbolics. All right, so that's y prime. The length we're looking for, integral from minus a, is it minus a? No, it's 0. Sorry. 0 to a. So what we're actually looking for, if you think of this as minus a, think of this as plus a, we're finding half of its length. That's typically how you would actually think of the poles being placed. The poles are placed at the minus and positive. And then right in the middle would be your 0 the axis. Square root of 1 plus this squared. So e to the x over a squared. E to the 2x over a, right? Take the product. What's e to the x over a times e to the minus x over a?
Is it 0? Or 1, I mean.
It's 1, e to the 0.
Yeah, e to the power of 0, but.
So we want to double that, so that becomes minus 2. Then e to the minus x over a squared would just be e to the minus 2x over a. And then all over 2 squared, 4. Dx. Again, this is looking pretty hideous. Write this as a single fraction. What's 4 minus 2?
2.
Look. Be negative. But e to the x over a and e to the minus x over a, they're always positive. So that value is always positive. Just that, right? Antiderivative of e to the x over a.
Is it a? X, e to x over a?
What about e to the minus x over a? Should be pointing over here.
Is it negative a?
That's going to be evaluated from 0 to a. We can factor out an a. To give us a over 2 times so a over a, e to the 1, right?
Yeah.
A over a again is 1, so this is going to be what? Minus e inverse. At 0, isn't that just e to the 0, which is 1?
Yeah.
Minus e to the 0. They cancel out. There's the length of a catenary curve. A over 2 times E minus E inverse.
Oh, so you just don't like do it, just gotta leave it like that? Or?
What do you mean don't do it?
Like if you actually went to evaluate, it would be 0, wouldn't it?
No, E minus E inverse is non-zero.
Okay.
Right, because E inverse is 1 over E.
Oh, okay.
Good on arc length? So when you talk about a two-dimensional object, just going to use rectangular because it's the easiest. Two quantities of interest. What are those two quantities? I'm talking about in general the entire two-dimensional object.
The perimeter and the area?
Right? The area. So essentially how much is there? And the perimeter. Which you can kind of think of as like a quote-unquote length. Right, so this area, how much is it enclosing? Perimeter is how much material do you use to create the object? How much wire do you use, so to speak, if you're fencing in? Look at a three-dimensional object. Again, I'm going to stick with rectangular because it's easier. Good enough for government work. There are again two quantities that we're interested in. Volume, how much is enclosed.
Surface area?
And surface area, how much is around. We looked at volume the past 3 days, right? The past 3 classes. Now we're going to do surface area. More specifically, in this class, surface area for a surface of revolution. You'll look at surface area more generally in Calc 3. So what is a surface of revolution? I'm so glad you asked. Take an arc of a curve and revolve it about an axis. Right, so we looked at solids of revolution before where we actually just did the entire region, right? Rotate, that gave you a solid. If all you do is take a curve, you get something hollow. and it's very thin, which means volume is negligible. You're getting literally just a surface. I could argue you can also find surface area of a solid revolution, right? Same idea. All you have to worry about though is when we go to integrate, really what we're just looking at is we're concerned only with the curve, nothing else. Because the surface area is going to be the same whether it's solid or hollow.
So this is basically just the line.
It's just the arc.
Okay.
Don't say line.
Or,
That's not a line.
yeah, curve.
It's a curve, an arc. I hate arc too because arc usually has a different meaning when you think of it as an arc of a circle. But technically we call any segment of a curve an arc.
Yeah, like not no shaded region.
Right.
Okay.
So you could hear it two different ways. I may say, what's the surface area of this solid of revolution? Or I may say, what's the surface area of this surface of revolution? It's done the exact same way. All you're concerned with, if I give you solid, is just the surface anyway. So again, f of x has to be continuous. Area of the surface obtained by revolving f of x over the interval a to b about the x-axis is, we use capital S for surface area. So I'm going to try and distinguish my S's from my integrals by putting lines. It's 2 pi times the integral from a to b f of x times the square root of 1 plus f prime of x squared. Very similar to arc length. In fact, we just take the integrand of arc length and multiply it by 2 pi times the function. And that gives surface area. You thought arc length integrals were a pain in the ass. These ones really suck. Because now you have that additional f of x there. And sadly, you usually can't get rid of that with u sub. These integrals suck. Even the simple ones suck. Find the area of the surface generated by revolving the arc of the parabola y squared equals 12x from x equals 0 to x equals 3 about the y-axis. About the x-axis. But first, let's think about this. Y squared equals 12x. Going to be something like that, right? So we go 0 to 3. So the arc we're looking at is that revolving about the x-axis. And so if you revolve that, you're going to get, it's called a paraboloid. Cup without a flat bottom, it's called. So a very useless cup.
Shouldn't f of x only be positive when where was like for
It doesn't have to be.
math is before? Or was it like for math is before? The volume.
Volume had to be positive.
Okay.
For arc length and surface area, it doesn't necessarily have to be. However, what if I just take half of this? Let's say I just delete that lower half. Do I still get a paraboloid?
Is it still revolving about the?
Yeah, still around about the x-axis. I just removed the lower half.
Yeah, you still got.
It's the exact same shape. So it's what? Y squared equals 12x. Without loss of generality, we can just say y is the square root of 12x. I could also do negative square root of 12x and get the exact same thing. We need y prime. rewrite this. Because square root of 12 is a constant, isn't it?
Yeah.
So I could do that, or I could also use chain rule. So this would be what? If I took the derivative. That alone, right, if I take square root of u, derivative, I'm sorry, 1 over 2 square root of u, right? But now I have to multiply by 12. That's just 6 over square root of 12x. But by the way, square root of 12, 2 root 3. So I can simplify this even further. Three over the square root of 4. Not 4x, sorry, 3x. Doesn't matter, just makes the arithmetic a little bit easier. Surface area. Integral over the interval 0 to 3, y times the square root 1 plus y prime squared dx. Y is the square root of 12x times the square root of 1 plus, now y prime squared.
Is that 3x or 3x squared?
3 over x, right?
Yeah.
This would be 9.
Mm-hmm.
This would just be 3x. Write that as a single fraction. Square root of 12 is constant. I'm going to factor it out. Oh my God, I always do this. Forgot something. I forgot the 2 pi in front. Thankfully, that doesn't mess anything up yet. Just add it. Integral from 0 to 3. Well, look, I factored out square root of 12, right? I'm left with the square root of x. Here I have 1 over square root of x. They're going to cancel.
Yeah.
All we're left with is the square root of x plus 3. This one is one of the very rare ones that works out quite nicely. So 2 pi square root of 12 times x plus 3 has a derivative of 1. We can just treat the entire x plus 3 as a single variable, call it u. U to the 1/2 antiderivative. Two-thirds u to the 3/2. X is 0 to 3. 4 pi root 12 over 3. Oh, right, okay. Yeah, I'm back. At 3, we get what? 6 to the 3 halves? Minus, at 0, 3 to the 3 halves? So I can simplify this, right, as 2 root 3. A pi root 3 over 3. Oh, by the way, root 3 over 3 simplifies.
8 pi over root
8 pi over root 3. That's not necessary. You could have kept it as root 3 over 3. This just looks nicer to me, so that's what I'm going with. 6 to the 3 halves. 6 root 6 minus 3 to the 3 halves is 3 root 3. Can factor out a 3, right? So that'll give me 24 pi over root 3. Don't root 6 and root 3 have root 3 in common?
Yeah.
We can factor out a 3 root 3. Then you're left with 24 pi times 2 root 2 minus 1. There is our surface area in square units. Find the area of the surface generated by revolving the arc of y squared plus 4x equals 2 log of y from y equals 1 to y equals 3 about the y-axis. So we can solve x in terms of y, and it's very easy to do, and that's what we're going to want to do. So start there. X is going to be 2 log of y minus y squared all over 4.
That's because we're doing it about the y-axis?
We're doing it about the y-axis. We need x prime. Well, again, that 1 over 4 is a constant. So it's going to be the derivative of the numerator over 4. What's the derivative of log y? So we get 2 over y minus 2y. Going to factor out a 1 over y, put it in the denominator. And that can also be simplified. One minus y squared all over 2y. There's x prime. Surface area. Integral from 1 to 3. X times the square root of 1 plus x prime squared. Oh yeah, say I always forget that bloody 2 pi. 2 pi. Times that.
That difference of squares up there.
After some algebra. You're going to wind up with this. Parentheses are implied. That's fine. No problem with that antiderivative. No problem taking that antiderivative. No problem taking that antiderivative. Two y times log of y. If you were to do it by hand, how would you have to do that? This first one is just a change of variable. Let u be log of y. 1 over y dy, done. That's just 2u. Both of these are simple power rules. What's that one? Give me hints, not calc 1.
Go to the chart.
I said by hand.
Oh, that means no table.
Right, no table.
We have to try to do it by parts or something?
That'd be integration by parts. Ain't nobody got time for that. I just use the CAS. I was very sad because I did all this algebra just to find out I had to do freaking by parts, and I said, yeah, damn that. And I wound up throwing it into a calculator, so I could have avoided all that and just come right here. And in fact, that's what I'm going to show you. Once I write out the solution, I'm going to show you how I can simply throw this into CAS. There's your surface area. So even this one, well, yes, integration by parts, it's not terrible. Right? That's definitely manageable. A lot of them, you're going to have to use Simpson's rule to get an approximation, because a lot of them cannot be done. At least arc length has fewer that you have to use Simpson's rule for. Surface area has a lot more. Which is why I can never write a textbook, because I could never find problems I can easily do by hand. All right, so here's what we can do. First thing that we're going to do define x of y. So define x as a function of y. And we said that was what? 2
ln
log of y
minus y squared.
minus y squared, and then all over 4, right? Again, remember in Mathematica, log is natural log. I technically don't need to do anything else. However, just to make sure that we get the work right, and again, I'm actually using it to print something so I can clearly see when I execute it that this is going to be x prime. So I'm going to say x prime is equal to, I can just do x prime of y. That'll give me the derivative. And then for surface area, doing this way now makes it really easy. 2 pi times integrate. We said it was x of y, right? Times the square root 1 plus x prime of y squared, right? With respect to y, with respect to y, and we go what, 1 to 3? So I don't actually have to worry about typing in the derivative by hand. Pi over 4 minus 28 minus 28. Log 3 times log 3 is log squared. 9 log of 3 is log of 3 to the 9th. And 3 to the 9th is 19,683. So much easier. What I would recommend you do on the exam, I would recommend you do that first step, the setup, so calculate the derivative and then set it up with the derivative and then use a CAS to evaluate it. Because remember, on the midterm, you're not going to be allowed to use Mathematica, only a calculator with no screenshots. So if you don't write the setup down, I'm going to have no idea if it was because your setup was wrong or you typed it in wrong. You just made a typing mistake on your calculator. I'm not going to be able to distinguish, so I'm going to go with the worst case scenario that you didn't know how to set it up. So I would recommend you actually write out the setup. You don't have to go all the way, right? You don't have to do the algebra and simplify and all that. At least get the setup so I know that you know how to set it up right. So we have, and this one's a bitch because it gives us A, arbitrary A. That's fun. So we have a curve. 8a squared y squared equals a squared x squared minus x to the 4th. We're revolving this about the x-axis. And it's one loop. So what we could do is come over here, do something very similar to the catenary. So let's just call this loop of A, plot. No, I'm not going to do plot. I'm going to do contour. 8a squared times y squared is equal to a squared times x squared minus x to the 4th. Let's go minus 10 to 10. We'll start with this. Turn off the frame and turn on the axes. And let's just look at loop of 1. Okay, so that's going to give me a general idea. I'm going to go loop of 5. So lemniscate. So they want to revolve one loop. So this here would be a loop, this one side. Revolving it about the x-axis, right? Well, if I revolve the entire loop about the x-axis, I would get the exact same thing as I just revolved this top portion about the x-axis, right? We go from what? 0 to A. If you do several of these, you're going to see that whatever A is, that's how far out it goes. It goes from minus A to positive A. Since I'm only going to do a quarter of it, right, I only need to worry about this part here. 0 to A. And it doesn't matter which loop I choose, right, because it's going to give you the same thing. So that's why, without loss of generality, I can take the right half. So that's why it's going to go 0 to A, and because I'm only considering the top half, y is going to be positive, we can then write this as y equals the square root of a squared x squared minus x to the 4th all over 8a squared. I would not recommend you try to take the derivative of that. Use implicit differentiation. It's going to be left to you to do. I'm not going to write out the whole thing. It's going to be left to you as an exercise. You can do this on the CAS, but do it by hand. Challenge yourself. Have some fun. That's going to work out to be a real sexy 1/4 pi a squared. Going to warn you, there is a lot of algebra doing this by hand. It's a good way to challenge your algebra skills too. Questions on surface area? You can now work on the 12th assignment. So remember, all that's going to be due March 13th, which is next Wednesday. Second discussion assignment is up. Has to do with reading an essay called A Mathematician's Lament. It's 25 pages, but it's not math heavy. In fact, I don't think there's really any rigorous mathematics in it. Right, and then you'll respond to the prompt. Initial posts are due the 8th. Responses will be due on the 12th. And I am allowing you a chance to fix the code and resubmit it on the 13th. So it's not required. But if you want to get a higher grade, you can fix the code and resubmit it on the 13th. Don't forget the midterm is on the 13th. And then we have spring break. Have a wonderful evening. Stay dry. Have a wonderful weekend. It's Wednesday.
Oh, yeah.
See you Monday. And if you haven't turned in the quiz yet, make sure you do so.
I'll send it. Yeah.